All right, so in this related rates example, it reads like this. A man 2 meters tall walks away from a lamppost whose light is 5 meters above the ground. Okay, so here's the guy, okay, I drew this guy right here. And here's the lamppost, okay, that's, 5 meters above the ground. And the man is 2 meters tall. Okay, so we start with the 5 there, and we have also the man that's 2 meters tall. If he walks at a speed of 1.5 meters per second, okay, so his speed, that's a rate, right? That's a rate of change. That's going to be a derivative. So a derivative of what? Let's keep reading. At what rate is his shadow growing when he is 10 meters from the lamppost? Okay, so we are talking about a distance from the lamppost, right? So if the distance from the lamppost is going to be x, then his rate of change, what he's moving, is x prime. Does that make sense?
Yeah.
So we're going to let the distance from the man to the lamppost, because that's what's referenced in the question later, right? When he is this many meters from the lamppost. So that's going to be at x equals 10. But his rate of change is 1.5 meters per second. Okay, x prime, or dx dt, the derivative of x with respect to time. Now, it says if he walks at this speed, what is the rate of his shadow? Now, where is his shadow? His shadow is actually from his feet, to this point right here where the light, touches the top of his head and it shines onto the ground. So this is actually the length of the shadow, which should be our second variable. See that? So the question is asking at what rate is his shadow growing? So the shadow is this length on the ground. So we're asking for y prime. That's what we don't know. All right, so remember with these related rates problems, what we're looking for is two rates that are related somehow. That makes sense.
Okay.
And we're also looking for at a certain point, so at a fixed point in the problem.
Okay.
So we're looking for two rates and at a fixed point. So we have this in this question. So this is the tricky part, kind of identifying this. But the lamppost is 5 meters above the ground. That's not any one of these. That's just a constant in the problem that's in the diagram. The man's 2 meters tall. That's not one of these either, because that's a constant. That doesn't change. But his distance from the lamppost will change because he's moving. So x equals, so y prime we don't know. We just established that. At what rate is his shadow growing? So that's the length of this shadow is y prime, we don't know. He is moving at, that's his rate of change over here, is 1.5. And what is the rate that his shadow is growing at x equals when he's 10 meters from the post? Okay? So setting up your diagram is important if you, to get this straight. Now we have to find out how these are related. Okay, this might be the tricky part. All right, but how are these related? So we do have some right triangles here, and it kind of looks like we might be dealing with similar triangles, right? So what can we set up a ratio? Like, for example, let's look at this smaller triangle, the length of the side to the length of this side, right, in a right triangle. So this would be, let's start with the y. Y over 2 is the same as what? What's the length of the larger triangle? So I'm looking at this larger triangle here. What's this length, total length? It's going to be x plus y. So x plus y is the length, is to 5. Are you following me there? Similar triangles, let's relate corresponding sides together. We could do it as x plus y is to y, as 5 is to 2. It's going to be the same thing. So if we try to now, let's try and fix this a little bit. Let's get rid of the denominators, cross multiply, right? And we would come up with, and I'll go back to blue here. Let's move over here. We come up with 5y equals 2x plus 2y. Does that make sense? And now we could actually combine the y terms together. That'd be kind of nice. That'd be 3y equals 2x. Okay? How's that? Is that good so far?
Yeah.
All right. So now we have a relationship here between x and y. And y and x here are the two related rates, so I'm going to now take the derivative of both sides. Does that make sense? So what's the derivative of 3y if I'm differentiating with respect to time?
3y prime.
Good. Well, it's going to be, it's going to be 3 times y prime. That's right. So the derivative of this would be 3 and then multiply by the derivative of the variable. What about this one? Same reasoning, 2x prime. Does that make sense?
Yes.
Okay. Very good. Now, what about, let's see. So 3 times y prime, 2 times x prime. Okay. All right. So we've got y prime is in there, x prime is in there, but what about x? How do I include x? How do I include x in here? So in this case here, when x equals 10, you see there is no actual x value in here, so it doesn't matter what the x value is. We just plug in our one rate that we're given, and we can solve for the other one. So that looks like this. 3y prime equals 2 times 1.5. Divide both sides by 3, we get 3 over 3. Now it should be noted, let's see, is it? No, that's all good. We didn't miss any signs. Sorry, y. That should be y prime. And blue. This blue is 3 over 3. So y prime equals 1. And what are the units there? Well, we're talking about the change. Length is meters, and the time is seconds. So it's just a length, so it's going to be meters per second as well. So, in the words, the shadow is increasing at a rate of 1 meters per second, or 1 meter per second. Okay, so that's how you do that one, and that's one where it appears that in this equation, or in this situation, that it doesn't matter how far this man is from the light post. It could be any x really, and the shadow would be increasing at the same rate no matter what. Yeah, so there you go.
Alright,